So the first one, obviously the most popular one is the force of gravity. So when we talk about gravity, we typically write it as F of G. And you're going to see that the most common way that people write the force of gravity is they write mass times the acceleration due to gravity. So what is this force? This is the gravitational pull of a planet on an object, right? So in our case, it's the gravitational pull of a planet like Earth on an object. So when I think about this picture here, what I really mean here is that I have Earth here. And what we know here is that right at the center of the Earth is where that force is pointed here. So if I take an object here, 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 or here, the force of gravity is always pointed towards the center of the Earth. No matter where that object is, the force of gravity will always point towards the center of the Earth. And so what we say here is that that's what the force of gravity is. Second one, let's go to the spring force. The spring force is probably the force that we will deal with quite a bit. And so typically we write the spring force as F of S. And I would say that without any doubt, this is one of the most common contact forces. So let's look at that. So we've talked about the push and pull of an object. So the example that I gave just a little bit ago, that you could imagine that I have a block, and these blocks here are going to be feeling a spring force. So if I have a spring like this, and let's say that there's motion in this direction, so that means that the object is moving in this direction. What's going to happen to the spring force? Well, if I'm compressing the spring, right, compressing, that spring is then going to apply a force in which direction? It's going to be in that direction. So in this case, it's a push on the block. On the other hand, you could imagine that I have a spring like this, where the motion is now in this direction. So I'm stretching out the spring. So in this case, you're stretching the spring. So what's the spring going to do? It's going to pull backwards. So in this case, there's a pulling this time. Now, it turns out that you can model many, many forces that look like this. So let's check this out. So now we can model numerous contact forces with springs. So let's look at this thing here. So one of the easiest way to model here is to really look at the atomic structure inside of materials. So what we'll do here is that let's look at atomic structure inside of a material. And what you find with this thing here is that you can imagine that we have a series of atoms, or whatever you want to call them, right? And when you're looking at these guys, what you're seeing here is that I could imagine that these guys are really a series of little tiny springs that attach to each other. And so when I'm looking at these little springs here, what I'm saying here is that we can model these as springs. So we model as springs the electrical bonds that forces materials to bond together. And so what you could find here is that if I push on one of these little red guys, so let's think about this here. So if I come in here and let me push on this center one right here. So if I push on this guy right here, what's going to happen? There's going to be a spring-like force that then moves in the opposite direction. Or if I come in here and I push right here, right? That's another push right here. There's going to be a spring force pushing back something like this here. So it's going to be a spring-like thing here. So here's what you find here. So if I look at the spring force here, it goes something like this. So if I push harder, the material pushes back harder. And if I push let's say, less, I should probably say less hard or whatever, but I'll just say less, then that means the material is going to push back less also. So that's really the basis for modeling almost all of the contact forces that I could think of offhand. Let me give you examples of this. Okay, so the two that are really important are the tension forces and what are called the normal forces. So let's focus on this. So now I have a tension force. And so the tension force I typically call T. Okay, so let's think about a rope now. So if I have a piece of rope or a string, what I imagine here is that I'm going to have a series of little atoms, right? So in other words, I'm going to be looking at something like this here. I imagine that I'm focusing on this atomic structure here, but now it's going to be tiny. So check this out. So here's my little atomic system. And each of these black ones are these little modeled springs here. So look what happens. So if I now pull on the rope, so if I pull, right? So if I pull on the rope in this direction, what are the springs going to do? If I pull them out, what am I doing? I'm stretching them. But if I'm stretching them, then the spring force is then going to pull in the opposite direction. So it pulls in opposite direction. Right? If I pull on it, right, it's got to be the opposite. So then check this out. Look what happens here. So now I have a box. Here's my handy little box. And now I'm going to put a rope on here. So here's my rope. So my rope is this guy right here. And as I look at this rope, what we're actually seeing here is that there's going to be a pull here. So you could imagine that I have my person, right? And this person is then going to be pushing or pulling on this rope right here. So as they're pulling here, what happens? The force of the person goes that direction, but the rope does what? It pulls in this direction, and this is going to be my tension force here. So as I pull this way, I feel the tension force in the opposite direction. And there's another example that I just thought about that we can do the same thing. What happens if I have a pulley here? So if I have a pulley system, let's say that it looks something like this. And there's the center, and what you're finding here, this is a pulley. So when I look at this pulley, I have a rope. Let's think about, in this case, let's think about a red rope. So you could imagine that this guy looks something like this here. And then what am I going to do? I'm going to attach my block again to this rope. So if I do that, look what happens here. If I pull with the force downwards, that means I'm going to pull on this rope, right? I'm going to pull on this rope, and okay, let me say this is the force of the person pulling down. As they pull down, look what happens. This thing translates because of the springs. It translates in such a way that what this box feels is now going to be what? The tension, which is in the opposite direction here. So there's the same type of thinking that's going on with that. Another very important force here is the so-called normal force. And the normal force I typically write as N. So let's go look at this guy here. Now, again, I want to model my force with springs here. So let's go look at this. So what you're going to find here is that anytime I have a contact force with the surface, there's two forces. I only want to talk about one of them. So any surface, maybe I should write this big, any surface contact force that is perpendicular to the surface is called the normal force. So how do I model the normal force here? So the picture that we want to do here is that we want to do the following thing here. So picture-wise, imagine that you sit on a bed, not a bed, but a bed of springs. Right? I have a bed of springs. So if you sit on them, what you could imagine here is that I could model my springs maybe to look something like this here. So when I'm looking at my dots, you could see here that I could come in here and I can draw my spring forces. And what you're seeing here is that if I come in here and I put a block on this thing, okay, so here's the block. So what you're seeing here is that if I have a surface like this guy is pushing up in the up direction here. So what do I mean by this here? Well, imagine that I have a tabletop. So here's my table. And what I'm going to put on my table here is I'm going to put two different blocks. So here's a smaller block, and then here's a larger block. So I'm thinking here's this block, and then there's that block right there. And what you're seeing here is that when you look at these blocks here, what you're finding out is that each of these blocks have different weights. So in essence, the smaller block, what you find here is that the springs bend less, therefore you get a smaller normal because it's pushing less on the springs here. However, so if I come in here and I draw my picture here, how am I going to draw it? Well, I'm going to come up here and I'm going to say the surface of that table then applies a smaller normal force. But now, because this is a bigger one, right? What I'm saying here is this compresses more. This implies that I must have a larger normal force. So when I go and I look at this guy here, this is bigger here. And it's bigger because it's bending the table more. Okay, so I probably should have put this more here just to be consistent with how I'm trying to write things. So it's the more compression that gives you the bigger than normal force here. So to sort of like stress this idea here of the normal force, we can also imagine that what happens if you go in and you push on the finger here. And so the scenario that I want to draw here to re-stress this idea, again, imagine that you have a surface here. Okay, here's my surface. And what I'm going to do here is I'm going to put two blocks. And then I have the exact same block right here. So when I'm looking at these blocks, what you're seeing here is that these guys are exactly the same blocks. So now what happens? Well, if this block is just sitting on the table, then what you're going to see here is that the normal from the table is pushing this block up like this, right? So this is how hard the table has to push up. Now imagine the following thing though. Imagine that I come over here with my finger, right? Right? So what I'm going to do here is that I'm going to, right here, you're seeing that I'm going to, oops, I'm going to get right in the way. So what I'm doing here is that I'm pushing down with my finger. So how do you expect the table to respond? Of course, you're going to respond by saying that the table has to work harder. So what you're really doing here is that you're compressing the springs more. So what this is telling you here is that the table has to work harder now. So the finger forces the normal to increase. The finger forces the normal to increase Because why? You have more spring forces that are being compressed. The more you compress a spring, the more it works here. So that's just the normal for a flat surface. But there are other normal forces too. And what I mean by that is that if you look at the normal forces, you'll find that one of the most iconic problems in physics is the inclined plane. So if you're looking at an inclined plane, and what you're going to do here is that you could imagine that you come in and you put in a block. So if I put in a block right here, look at the direction of the normal force. It has to be perpendicular. So what's it going to do? The springs are pushing perpendicular to the normal here. What about if I have a vertical wall? Right? If I have a vertical wall, and if I put that block on this vertical wall, and then all of a sudden what I'm doing here is that I'm pushing on that wall, pushing on that block. So what you're going to see here is that in this case, that wall has to do what? It has to push in this direction, perpendicular to the surface here. Or what if I have a ceiling? If I have a ceiling here and I have a block, that normal force is not going through the ceiling. Why is it not going through the ceiling? Because the normal force is pushing perpendicular. So at every junction, the normal force means perpendicular to the surface, perpendicular to the surface, perpendicular to the surface. So resistive forces. So when we talk about resistive forces, it's a force that opposes motion. So any force that opposes motion is called a resistive force. And it turns out that there are two types. There's surface resistive forces, and there's fluid resistive forces. Okay, so let's look at this thing. So any surface always has two forces. One of them we talked about the normal surface force is perpendicular. And that's what we just talked about a moment ago. But there is a parallel surface force. And the parallel surface force is parallel to the surface. And this parallel surface force is what we typically call friction. So a parallel surface force is friction. And so let's think about this thing. So imagine that I have a surface. Okay. And on the surface, I have a block. So I imagine that I have my block right here. And now when I'm looking at my block, I imagine that this block is actually moving in this direction. So the frictional force always opposes the direction of motion. And friction is symbolized by the little symbol F. So then we write F is in the opposite direction of this thing here. So what do we know about electrical forces here? Well, one of the things that frictional forces. what you find here is that this is the floor, and then this, of course, is our block. So to really understand what friction is, we look at the molecular surface between block and floor. And what you find here is that when you look at the structure of that surface here, it's actually quite jagged. So you could imagine that this, at this level, this guy here is the floor at the surface that we're talking about. On the other hand, when you look at the block, you also have jagged stuff like this. And so when you're looking at this surface right here, this guy here is the block. And what you're seeing here is that what you get in between these two surfaces here is that you get an electrical molecular interaction. And when you look at friction at this level, it is outrageously complicated. And you have to really be careful about the models that you try to explain what is going on. But so what you're finding here is that when we ask in detail, what is friction? This friction, okay? That is friction. It's this molecular interaction between these atoms, and different materials have different interactions, and so therefore friction is different between two different objects. So you can see here is that this green block is sliding in this direction, then the peaks of the green ones are interacting with the peaks of the black ones. And so you have this relative motion between the two surfaces here. And it's this peak interaction that effectively gives rise to friction here. And what we find here is that there's two types of friction. There's one of them is called kinetic. In other words, moving. Maybe I shouldn't say moving. I should say, when I say kinetic, I really mean sliding friction. And we typically symbolize this F for friction, and then we write a little k to tell us that we have this moving friction here. And what's special about this force here is that that this frictional force, so F of k is equal approximately to a constant. So sliding friction, kinetic friction, involves motion and it's constant. Then we have the second kind of friction, right? Static, which means it's random. And when we write this, it's typically symbolized with the S. And what you find about this thing, this is the really strange thing. Static friction is actually a variable force. And I should have said that this is approximately a constant force. And in the next chapter, we'll spend more time in trying to do that. So we talked about two types of friction. One type of friction up to this point. We said surface resistive forces. That's the kind of friction that we talk about every day. Now we have a fluid resistive force. And what you find next is that there's another type of friction called drag. And in fact, our next two labs are on this drag force, which is typically symbolized D here. This drag force, this here, it's a resistive force. the resistive force of an object moving through a fluid. And there's many fluids that we could think of here. The two most common ones is, of course, air resistance, the drag force of air, and the other one is water. And so what you're going to see here is that in our next lab, by the way, just to make sure that we're clear about this, outside of the physics stockroom in the 800 building we have a big box there, and we've put out numerous coffee filters and Hot Wheel cars. So if you're interested in picking up coffee filters, you'll see that you'll have to get a stack, and we're going to look for I think you're going to need 5 coffee filters, but that's to set up for the next 3 labs here in case you need those things. Okay. Yes, air resistance is the same as this drag force. So drag and air resistance are exactly the same. Is that what you're going to do here is that we have these big coffee filters. And when you're looking at these coffee filters, you're going to drop them in air. And what you find here is as you drop these in air, what you'll see here is that you have air molecules. So as this thing falls, what you're seeing here is that you're getting numerous collisions with the air molecules. So what you're finding here is that air drag is due to the numerous collisions between an object and the air molecules. Okay, so you have numerous collisions between these guys, and that's what produces that. The same thing if you're moving through water.